So today we're talking about the very famous bleeding llama flaw in LLaMA. LLaMA, as you know, is a very popular tool for running AI models on your hardware. So in this flaw, what happens is if an attacker uploads a single file to an AI server, and that file doesn't have to be a prompt or a script, it could just be a model file, which is the kind of files that these servers load every single day. And a few seconds later, the attacker could just walk away with the server's memory, which will have the API keys, database passwords, every user's private conversations, and the system prompts of every model running on the machine. So the attacker doesn't have to run any code, and they don't have to crash anything. And even the system will not log anything as wrong. And like I said, this is the famous bleeding llama attack. You probably have heard about it. And LLaMA, like I mentioned, is a very popular tool for running AI models on your own system, hardware, or server. And it has more than 170,000 stars on GitHub and more than 100 million downloads. And this CVE is numbered as 2026-7482. And at the time of disclosure, roughly 300,000 LLaMA servers were exposed on the internet. And we'll take apart the bug in this video, which is the file format, the exact out-of-bounds read, and the 3-request attack chain that happened. And then we look at why running your AI models locally just for the privacy can turn out to be a wrong thing to feel safe about. Everything in this video comes from the researchers at Sierra and the public advisories. And all of these flaws are fixed in the version 0.17.1 of LLaMA. But what I've done is I've taken all of the publicly available information and distilled them into these nice diagrams. So it's going to be a highly visual video. Make sure you watch it till the end. Now, you probably might have used LLaMA to run LLMs on your own machine. And instead of sending your data to a cloud API, you're basically just running it on your own machine. And companies use this exactly when their data is too sensitive to send out to an API like a OpenAI API or Anthropic API. So they run these models locally and they feed them proprietary code, customer contracts, and internal documents. And that's the first thing that's important. LLaMA server is in a place where secrets are piling up fast, and it has API keys and credentials in its environment so it can reach other systems very easily. Now, to be able to run those AI models, it obviously needs to hold system prompts of all the models that have been loaded into LLaMA. And it also processes a stream of mostly private user conversation. And all of that lives in the server's memory while it is running. And this attack can steal all of those secrets and keys right out of that memory. Now, to run a model, LLaMA just loads it from a file, and the standard format is called gguf. And a gguf file is just a container. It holds the model's weights, which is the giant grids of numbers that make up the model, plus some metadata that describes the model. The important part in the model is the tensors. The tensor is one of those grids of numbers, and the file stores two things about each, which is a header that declares the tensor's shape and size, and then the actual block of raw bytes for it. And the header says something like this, that, hey, the next tensor is actually this big in size, and then the data actually follows. So if you think about it, a gguf file is basically a series of promises. The header promises how much data is coming, and the data is supposed to match that header. And this vulnerability is what happens when the file lies about the size of the data, because when the header promises more than the file actually contains, that can lead to the vulnerability. And the entire model is just a gguf file, and anyone can handcraft a file if the model is just a file, right? Now, when LLaMA takes in a gguf file, it can quantize the model, which is basically converting the numbers from one precision to another. And for example, it can turn 16-bit floats into 32-bit floats. It's routine model handling. It runs when you create a model through LLaMA's API. To do that conversion, the code reads each tensor's bytes out of the file and processes them. And here's the decision that matters. To know how many bytes to read, it trusts the size declared in the header, and the header says the tensor is a certain size. So the code sets aside a buffer and reads just those many bytes. Now it trusts this information that the header is giving it. It never checks it against how much data the actual file actually contains. And that missing check is the bug. So the attacker is basically exploiting this little lack of check. So they craft a gguf file where a tensor's header declares a huge size, say 8,000 bytes, but the file actually contains just a couple hundred bytes of data for it. So LLaMA reads the header and believes that the tensor is actually 8,000 bytes because the header says that. So it goes on to read 8,000 bytes, but only a couple hundred bytes are actually there. So it reads past the end of the real data and keeps going into whatever memory sits next to it. So this basically is the out of bounds read. So after you've read through the entire data, the real data, which is 200 bytes, but you're going for 8,000 bytes. So it's going to keep reading into the other prompts, the system prompt, the API keys, the database credentials and tokens, all of that information that was never supposed to read. It's able to read through all that information in memory. So let's understand how this happened, because this is a common pattern, right? The original model loading code was written in C++. It was tracking how many bytes were actually left in the file and refused to read past that limit. And every read was basically checked against the real length of the file, and an overread would just fail cleanly. But LLaMA's version was written in Golang, and that rewrite used a file reader that does the wrong thing here. When you ask it for more bytes that remain, it doesn't produce an error. It just fills the rest of the buffer with whatever was already sitting in that memory. So the code allocates a buffer based on the size that was mentioned in the header, and it asks for the full amount of memory, gets a little read data and a lot of stale heap memory, and treats all of it as the tensor data. The safety check that existed in the original version was simply not carried over to the rewrite in Golang. So the bug is nothing special. It's just a bounce check that got lost in translation between the previous version, the C++ version, and the Golang rewrite version. But there is one detail that turns this into a more serious attack. Quantization normally changes the numbers because that's the job of quantization. And if the stolen memory got mangled by the conversion, the attacker would usually get garbage. So the attacker actually picks the conversion that doesn't lose anything. They use 16-bit float up to 32-bit float, and going to a larger type is lossless, and every original byte is preserved exactly. So the leaked memory heap passes through the conversion untouched and stays in a perfect readable condition. And the stolen secrets can come out of the other side intact character for character. Now, if you want the file with all of these diagrams, the Excalibur files, you can get them in the link in the description for free. And also, if you want to try out these kind of attacks in a safe environment, that's what we build at the Armor Dojo, where you have these independent labs where you can run these attacks on your own system in a safe sandbox and try them out on your own. So let's look at the entire attack, and it's actually a really short attack. It's just 3 requests, and none of them are authenticated because there are no endpoints that have authentication at all. So first, the attacker uploads the crafted GGUF file, the one where the header lies about the tensor information, to the server's upload endpoint. The second step is that they call the create endpoint to build a model from it and ask for the float 16 to float 32 conversion, and that triggers the out of bounds read. LLaMA overreads and scoops up all the neighboring heap memory and folds it into the resulting model artifact. The third step is that LLaMA has a built-in feature for sharing models. It's a push endpoint that uploads the model to a registry. The attacker points it at their own server and pushes, and the model, now stuffed with stolen memory, gets uploaded straight to the attacker, and they open it and read out the secrets. So it's upload, convert, push, 3 calls, and directly to the attacker's registry. So there's no password required, and the theft is complete. The reason this is so damaging is because of a property of heap memory. It keeps its contents across requests, so the program reuses the same pool of memory over and over, and old data lingers there until something overwrites it. So the leak is not limited to one moment. It can expose anything the server has handled since it last restarted. And in practice, that means the prompts, the chat messages of every user who's used the server, and the system prompts of every model loaded onto it, and the environment variables, which on a real deployment routinely hold API keys, database credentials, cloud secrets, and authentication tokens. And one researcher even noticed that from a company's AI server, you can learn almost anything about the company, its keys, its code, and its customer data. And if you repeat the 3 requests, you just keep pulling fresh memory every single time from that company. Now, they introduced a fix in the version 0.17.1 of LLaMA, and this included the check that was missing. So before reading a tensor, you verify that the size that the header declares actually fits within the file. And if the file doesn't hold that many bytes, you just reject it instead of reading into whatever lies beyond. So the information from the header actually gets checked. So if you've been running LLaMA, then patching is only the first step, because with this kind of a memory leak, you have to assume that any internet exposed server already gave up its secrets. So make sure to rotate the API keys, tokens, and credentials that were in its environments. Then make sure to put it behind authentication or a gateway, and don't leave it listening on the open network. So here's the main idea or takeaway from this video. It's that companies run LLaMA precisely because they don't trust the cloud with their sensitive data. And that's why they want to keep the AI local because it's private. But bleeding llama is the counterexample. So keeping the model on your own hardware moved the data closer, but didn't make it any safer. It just put all those secrets into a server that would read past the end of a buffer and hand them to a stranger. There's another lesson here. A model file is basically untrusted input, exactly like a network packet or an uploaded document. The moment your server parses a file whose contents an attacker controls, Every field in that file is an attacker's field, including the ones that just mention how big the file is. Just like in the case of Bleeding Llama, we had the header file telling us how big the file is going to be. So LLaMA trusted the header to tell the truth about its own size, but that trust was the whole bug. So just to summarize, Bleeding Llama CVE is about a crafted model file that declares in the header that a tensor is bigger than it really is. So the server reads past the data into its own memory and leaks all of that memory in just 3 requests. It didn't require a prompt or any code execution. It was just a file with a missing bounds check. Now, creating these attack path deep dives takes a lot of research and a lot of time to build these diagrams. So make sure you subscribe to this channel and share this with your friends and like and comment on this video. I'll see you in the next video. Thank you so much for watching.